Today we're going to be discussing Chapter 18, Sample and Distribution Models. For Chapter 18, you need to make sure that you have the simulation notes online here, giving us our sample and distributions for p hat. And this is with sample size n equals 5, n equals 20, n equals 100. So if you were in class, you would do a simulation where you would find the number of Razorbacks you get. So you'd be given these two plastic pigs or one plastic pig, and if it lands on its feet, it's known as a trotter. If it lands on its back, it's known as a Razorback. So we're going to see the proportion of Razorbacks we get in our sample. And this is our sample and distribution for when I did it before. So Chapter 18, Sample and Distribution Models. If you toss a pig 5 times and compute the proportion of Razorbacks, this is called a sample. The population is all possible pig rolls. The parameter is the true proportion of Razorbacks in the population P. Our population standard deviation is sigma. In our sample, the sample is 5 pig rolls. The statistic is the proportion of Razorbacks in the sample, which is P hat, and our sample standard deviation is S. If each person in the class tosses a pig 5 times and each person computes the proportion of Razorbacks in the tosses, and then we graph all of those proportions, this is called the sample and distribution or sample and model. All of the proportions are now our data, and that is what we have here. Sample and distribution, the distribution of values taken by statistic in all possible samples of the same sample size from the same population. Mu p hat is p for our sample and distribution. Our standard deviation of p hat is sigma p hat, which is the square root of p times 1 minus p all over n. Remember, 1 minus p is also known as q. If the mean of the sample and distribution is equal to the population parameter, then the statistic is an unbiased estimator of the parameter p. If you don't know p, use p hat, and this gives us what we call the standard error. So the standard error of p is the sigma of p hat, which is the square root of p hat times 1 minus p hat all over n. Remember, 1 minus p hat is the same as q hat. Let's look at our examples. What is the sample and distribution for the proportion of Razorbacks when n equals 5? So we need to find mu of p hat using our data from this page here. So mu of p hat would be 0.161 because that's what x bar was. Our standard error of p hat would be the square root of 0.161 times 0.839, all divided by n, which was 5. And that is about 0.164. For n equals 20, mu of p hat would be 0.167. My standard error of p hat would be the square root of 0.167 times 0.832, all divided by n, and n here is 20, which would be about 0.0834. And then as I increase n, I get 0.163. My standard error, as you notice, it's going down, so it should go down as I increase my sample size. And I have 0.163 times 0.837 all divided by n, and in this case, it was increased to 100, and that equals 0.0369. When is it okay to use the normal model to answer questions about population based on a sample and distribution with proportions? Conditions. So these are the conditions you would have to state. The randomization conditions. Sample should ideally be a simple random sample. At the very least, the sampling method should be unbiased, and the sample should be representative of the population. The 10% condition. N cannot be larger than 10% of the population. Population is greater than 10 times N. This condition helps ensure that the data is independent. So you can always say that N is less than 10% of the population of whatever is within context. And success failure condition. N times P has to be greater than or equal to 10, and N times Q has to be greater than or equal to 10. We must have at least 10 successes and 10 failures to ensure the sample is large enough. So let's look at these examples here. Is it appropriate to use the normal model to describe the sample and distribution of the proportion of Razorbacks when N equals 5? Why or why not? So all we have to do is look at N times P, and this would be 5 times 0.161, which equals 0.805, which is less than 10. So we cannot use the normal model because we expect fewer than 10 successes. Let's look when N equals 20. So again, you find N times P first. This would be 20 times 0.167. And we would get 3.34, which is less than 10. So again, we cannot use the normal model to describe the sample and distribution because we expect less than 10 successes. Let's look at 3. Is it appropriate to use the normal model to describe the sample and distribution of the proportion of Razorbacks when N equals 100? So first, let's check out N times P, which equals 100 times 0.163, which equals 16.3, which is greater than 10. Good, that works. And then we need to also check N times Q, 100 times 0.837, which equals 83.7, which is greater than 10. So our sample is large enough. Also, our pig tosses are random. And 100 tosses is less than 10% of all pig tosses. So we can use the normal model to describe this. So using the 68, 95, 99.7 rule, describe the proportion of Razorbacks when N equals 100, sketch the curve. So here, when we go ahead and do this, we have mu of p hat equals 0.163. Our standard error, which is the same as the standard deviation, sigma of p hat, is 0.0369. So when I'm describing this using my normal model, here we have our mean in the middle, which would be 0.163. And then 1, 2, 3 standard deviations to the left and 3 standard deviations to the right, since we're using the 68, 95, 99.7 rule. I'm going to go ahead and label 1 standard deviation to the left and right with pink, and those are going to be described in pink. I would add my standard error to get the one to the right, and I'd have 0.1 999. I would subtract to go to the left, and I'd have 0.1261. And then next we're going to do 2 standard deviations. So I'm going to go ahead and use red to color code this. And I'm doing this so that I'm not like squeezing everything in here. So I would add another standard deviation to 0.1999. I'd get 0.2368. And again, I would subtract on this side, and I get 0.0892. And then last, I would add another standard deviation, and I'd get, I'm going to leave this one in blue, 0.2737. And subtract on this side, and I get 0.0523. So we're going to describe the proportion of razorbacks when n equals 100, sketch the curve. So how I can describe this, if I'm looking at 68%, so 68% would be within 1 standard deviation. So this would be 68% within here. Okay, so I could say 68% of our sample proportions will be between 0.1261 and 0.1999. Then you can go ahead with 95% and say the same thing. 95% of our sample proportions will be between 0.0892 and 0.2368. And lastly, you can say 99.7% of our sample proportions will be between 0.5 to 0.0523 and 0.2737. Now, what would happen if we increased n to 100? So if we increase, or not 100, 1,000. So let's just ask C, what would happen if n would equal 1,000? Hopefully you would say it will still be a normal model. Centered at the true proportion. But the standard error will be lower. Now we're going to use this sample and distribution for Y bar. So the mean age of pennies of 1,000 pennies. Okay, so the mean age, this is when n equals 1,000. So we're going to use this data when we talk about n equals 1,000. This data when n equals 5, n equals 20, and n equals 80. So sample and distribution models for means. If you take a random sample of 5 pennies and compute the average age, this is called a sample. The population is all the pennies. The parameters, the true mean age of all the pennies, mu, with the population standard deviation being sigma. The sample is 5 pennies. The statistic would be the mean age of 5 pennies, which would be X bar, and our sample standard deviation would be S. If each person in the class takes a random sample of 5 pennies and computes the average age, then we graph all of these ages. This is called a sample and distribution or a sample model. All of the mean ages are now our data. Sample and distribution is the distribution of values taken by the statistic in all the possible samples of the same size from the same population. Here, my sample and distribution would be mu of X bar, which equals mu, standard deviation of X bar, which is sigma over the square root of n. And if the mean of the sample and distribution is equal to the population parameter, then the statistic X bar is an unbiased estimator of the parameter. If you don't know p, then use p hat, and this gives us what we call the standard error. So the standard error of X bar is S over the square root of n. The central limit theorem. The normal model approximates a sample and distribution when samples are large, or the mean for repeated samples will tend to follow the normal model as the sample size gets larger. When is it okay to use the normal model to answer questions about a population based on a sample and distribution with means? One, when our conditions is the random sample condition or an unbiased representation of the sample. The 10% condition, when n is less than or equal to 10% of the population, and a normal population or large enough sample. So the central limit theorem will take effect. Let's look at this example here. A sample is chosen randomly from a population that was strongly skewed left. Describe the sample and distribution model for the sample mean if the sample size is small. So take a minute and think about that. Hopefully you'd say something like the sample and distribution model will be skewed to the left. Okay, so it's skewed to the left, like the population. The mean of the model would be equal to the population mean. The standard deviation would be equal to the population standard deviation, but divided by the square root of n. So you would say something like sampling distribution is skewed left. The mean of the model would be equal to the population mean. The standard error would be equal to the population standard deviation. And divided by the square root of n. So you'd have standard deviation of x equals sigma over the square root of n. If we make the sample larger, what happens to the sample and distributions models shape, center, and spread? The shape will become more symmetric. The center will stay the same. And the spread, the standard deviation will decrease. As we make the sample larger, what happens to the expected distribution of the data in the sample? And hopefully you would think something like the distribution will resemble the population distribution. So the sample distribution will resemble the population distribution. The weights of newborn children in the United States vary according to the normal distribution, with mu equals 7.5 pounds and sigma equal 1.25 pounds. The government classifies a newborn as having low birth weight if the weight is less than 5.5 pounds. What's the probability that a baby chosen at random weighs less than 5.5 pounds at birth? So here, let's draw a picture of this first. So it's the normal model. With our mean 7.5. And we know that 5.5 is less than 7.5, so 5.5 would be here. And we're finding this probability that we have in purple. Okay, so we can standardize this. And remember that that would be x minus x bar all over your standard deviation, which is about negative 1.6. So the probability that z is less than negative 1.6 would be normal CDF. If you put it in your calculator, just remembering how to do this, negative 1e99 to negative 1.6, which would be about 0.0548. So there's about a 5.5% chance of a newborn being of low birth weight. You choose 3 babies at random and compute the mean weight, y bar. What is the sample and distribution of y bar? So the sample and distribution is normally distributed because the population is normal. The babies were chosen randomly, and there are more than 30 babies in the US. So our sample size of 3 is less than 10% of all babies. And the mean would be 7.5 pounds. With our standard deviation, we would need to find. So standard deviation of y bar would be 1.25 divided by the square root of 3, which is our n, which is about 0.722. So our standard deviation would equal 0.722. What is the probability that their average birth weight is less than 5.5 pounds? So this is with our 3. So we would again have 7.5. 5.5 is over here. We're finding this probability here. We need to standardize our score. So 5.5 minus 7.5, all over our standard deviation of 0.722, which is about negative 2.77. So the probability that z is less than negative 2.77, putting that into our calculator, normal CDF of negative 1e99 to negative 2.77 is about 0.00280. So there's a very small probability. So there is a 0.28% chance the mean weight will be below 5.5 pounds. Would your answers to A, B, or C be affected if the distribution of birth weights in the population were distinctly non-normal? Yes. The normal distribution would not be able to be used. The sample size is too small for the sample and distribution to be normal. Okay.